Princeton University, and he's going to talk about two-dimensional Luttinger liquids in a Moiré superlattice. And Dr. Wu, whenever you are ready, you can proceed.
Can you hear me now?
Yes.
Okay, good. Do it again. And you see my slides?
Yes, perfect.
Okay, cool. Make sure I have the spotlight. Okay. Well, thanks, Charles, for introducing me, and also Fan for inviting me. It's a great pleasure to share with you our recent results, even though it's a Zoom, right? But I would like to, it's a great opportunity to discuss with all of you. Thanks for being here. So my talk will be our recent results. So let me move my Moiré superlattice of twist tungsten ditelluride, and I will try to explain this title. What do I mean by one-dimensional Luttinger liquids? Actually, as my introduction, and then I'll talk about the experiment. Sorry, my slide's not advancing. It was working.
I think you have to use the, you cannot use keyboard to proceed. You have to use the cursor.
Oh, okay. But let me do this way. Now you can still see my screen, right? I thought I'm expert on Zoom. No, now it's better.
Yes.
Okay. Good. So let me first, remind you what do I mean by to talk about Luttinger liquid. Let me first remind you its counterpart. It's the Fermion liquids, which we are familiar with. It's really a amazing theory, right? Which is developed by Landau, which is a foundation of our understanding of interacting metals in condensed matter physics. It's very kind of surprising and amazing that you have a lot of electrons in the material, right? They certainly interact with each other, but at the end, Fermion liquid theory says don't worry about interaction, you just renormalize them. The electron mass, you still think about as if you have a free electron gas. And this Fermion liquid theory describes majority. It's also a very surprising fact that the theory describes majority of the metals that we know. And also it's the foundation to understand quantum phenomena in metals like non-dot quantization and superconductivity, right? So the non-Fermion liquids is unusual, and we know nowadays more and more examples of non-Fermion liquids are being discussed. It's not in the comfort zone of condensed matter research, and there are many kinds of non-Fermion liquid, but the fact that we still call them non-Fermion liquids means we do not understand very much of many of them. One of the typical example of non-Fermion liquid is the Luttinger liquid. In this case, it's only it's due to the dimensionality that you talk about metallic state in a one-dimensional system. If you have interaction in the one-dimensional system, the Fermion liquid description breaks down. You already see from here in the slides here that 1D system is special compared to 2D or 3D. If you have a think about a single parabola, and the Fermi surface here is only 2 points, right? So in a 1D system, even a very weak interaction will lead to very strong correlations that leads to the breakdown of the Fermi liquid theory. You can visualize this effects here in both real space and momentum space. In the real space, for 2D or 3D system, if you want to do some perturbation to the metallic states, let's say you add electrons to the system, then only locally you have the electrons next to the perturbation will kind of know that you're going to do the perturbation. But in one-dimensional system, it's not that case. If you want to add electron to any spots in a system, then the electron have to make a room for the next one, the next one have to make agreement with the other one next. So at the end, it's a collective behavior, even though you have you want to do just small weak perturbation, can be collective. Also in the momentum space, where I'm plotting here is the excitation spectrum as the shaded regime. In the 2D, you can have, for low energy excitation, you can have any associated momentum Q between 0 and 2kF, as you can see here. Right? You can shrink the vector Q vector by any size between 0 and 2kF. You can have excitation close to 0 energy, but not that this is not the case for the 1D system, where for low energy excitations, you can only have momentum Q and 2kF. Right? You can already see it. And near the 0 momentum, 0 energy, you have a well-defined dispersion relation. That's really an interesting case that if you include interaction in the system, you will end up with this Luttinger liquid theory, where the phenomena is very different from the Fermi liquid theory. And there are two outstanding, as you may already know, two outstanding phenomena. One is the power law suppression of the density of states at the Fermi surface. This means that you are no longer, the adding of electron, for example, or small perturbation is no longer easy. You have to pay energy. If you don't bring energy, you cannot add, the probability for adding these electrons becomes 0, which is not the case for the Fermi liquid. So this suppression of density states at Fermi surface can be described by a power law, where density states proportional e to the eta. Here eta is the power law exponent determined by the interaction in the 1D system. Right? So we also know, even though now you can add electrons to the system, right? You pay some energy, you get electron into the system, or take an electron out, the electron no longer behave as a single free electrons. Instead, you have fractionalization process that separates spin and charge degree of freedom. So you really even at the cartoon here is showing that you take one electron out, you're gonna excite two separate excitationally, and they behave independently, so as if you have fractionalized particles. So those are the phenomena of Luttinger liquid in 1D system, and has been in theories well developed in experiments, has also been widely observed in a wide range of experimental systems, including carbon nanotube, nanowires, and engineered quantum wires based on 2D system, right? and the topological edge mode, also Quasi-1D organic conductors. So this is really the property of one-dimensional system. The question I want to ask today is, can this kind of Luttinger liquid physics exist in two-dimensional system? If that's the case, so you really break the boundary of this dimensionality. You talk about a special kind of 2D non-Fermi liquid that mimics a Luttinger liquid. It's a very interesting question, because if you say yes to this question, you can ask follow-up question and say, right, what happens if you further, let's say, can you have superconductivity in a system? If you do, that's unconventional, because there's no Fermi liquid to start with. If you have, can you have non-dot quantization type of phenomena? If you do, unconventional, right? So what's the effect of spin charge separation and so on? So those are exciting questions. And of course, it's not the question that's, asking about 2D Luttinger liquid is not new. Is that actually first brought up by Phil Anderson decades ago, where he tried to explain the unusual phenomena in cuprate. He tried to argue that possibility of this two-dimensional Luttinger liquid in cuprate system, but of course this is a very challenging problem and very exotic concept. It's not established, even though he tried very hard. He wrote like more than 10 papers on this topic. Another question, which is kind of less exotic, but it's more straightforward, is to ask, can you have Luttinger liquid survive? It's not like completely emerging out of something like what Phil Anderson is thinking about, but can you ask, can you have Luttinger liquid survived if you put one-dimensional system, which means you start with Luttinger liquids, put them together to form a 2D system? That means that the easiest case is like this: you put one-dimensional wires in parallel to each other and then turn on the coupling between them, right? So that you turn the system into 2D. But by the time you turn on the interaction between the wires, system become 2D, the non-Fermion liquid physics become preferred, right? But the question is asked, in this case, can you find some interesting case where you turn on the interaction and non-Fermion liquid physics still survive? So that's a very interesting question. And you can look at this system. It's called couple wire models. You can look at this system more carefully using this picture that I'm showing here. So now you can replace the wire with the lattice. At the end is the crystalline lattice. So the electron can hop between sides along the wire. So in that wire, so the hopping is T parallel, which is big compared to the interwire hopping T perpendicular, right? And in the anisotropic case, which that mimic this couple wire model, means T perpendicular is much less than T parallel. And then you can ask, do you have Luttinger liquid physics? And you do when you have a temperature that's in between T perpendicular and T parallel, right? Because if you have a temperature high compared to T perpendicular, essentially you are saying T perpendicular is not important. So the temperature effects dominate so that you have thermally excited Luttinger liquid, right? So the physics still looks like 1D. However, it's not zero temperature, it's thermally excited. So what happened is that what is the expectation will be you reduce the temperature until you're reaching T perpendicular, right? And then you're gonna see the 2D physics where most likely you're gonna kill the Luttinger liquid physics. So you have a crossover temperature scale that's relevant to the T perpendicular. However, as I mentioned to you, hopping between Luttinger liquids is not easy. You have to pay energy, which means if you turn on the intra-wire interaction, means you saying there's a strong interaction in the wire, in each of the wire, the Luttinger liquid physics become important. Then this Luttinger physics will suppress the tunneling between the wire because you essentially try to add electrons to the wire, and that's not preferred. And so that the interaction will suppress this crossover temperature T star, right? So that's kind of understood in the study of quasi-1D organic conductors decades ago. So here's the formula here where eta is interaction strength. If eta is big enough, T perpendicular over T parallel is small, right? If eta is 1, then you have suppressed T star to 0, so completely. And you have something like this. You turn on the interaction, even though you have T perpendicular, but the crossover can be suppressed. If eta is large enough, you can completely suppress it so that you can say, oh, single particle hopping in this case is not relevant. So the Luttinger liquid physics may survive. However, in reality, you still have to consider two-particle process, right, and so on. So this indeed the problem has been addressed in early 2000, where I have selected a number of papers here. They really aim to sort of investigate the phase diagram of this kind of coupled wire models. And the finding here is very interesting. What they find that if you include interactions, you will be able to find the conclusion from the theory papers. There's a possibility that you will find a Luttinger liquid physics survive down to 0 temperature. Means that both single particle hopping and the two particle hoppings are all irrelevant. So the physics in this coupled wire model is still like Luttinger liquid. They call this sliding Luttinger method. Of course, there's another important aspect, which is that this existence. So what I'm showing here, the plot is a phase diagram. Lambda 1 and lambda 2 is the parameter used in the interaction parameter used in the coupled wire model. The existence of this phase is very narrow in the phase diagram. So majority of the parameter will give you either Fermion liquid-like phases or gapped. So you have to really tune the parameter to get this Luttinger liquid phase. So that's my background review of the the topic that I want to talk about. We in the last 2 years or so, we work on the experimental system that it's not that we know this all theory. It's kind of we have the experiment and then we can come back to relate all this background. And that's been.
Sanfeng, may I ask a question before
Yes.
you go to your experimental part?
Yes.
In the last slide, in the very end, what do you mean by two particle interwire hoppings?
Right. So in the argument I have there was simply like single particle hoppings. But you say 2 electron hop together, that's not included in my simple naive picture in the beginning, right? But those papers include them. So that at the end, the final state may be, for example, charge density wave. Those are strongly correlated, gap states or other things. So you have to include interaction more than 1 particle hopping. So the conclusion.
Okay, so basically the 2 particle interwire hopping is really part of the interaction, right?
Yeah.
Okay,
right.
I see.
So you have to, right, and then you have to massage the interactions, so that's to keep this Luttinger liquid survive.
Okay, gotcha. Thank you.
Right. So not all, majority of the type of interaction will cure it. That's why so you have very narrow shaded area here. This exists. Okay. And those papers are really try to include all possible, because in 1D you can classify it, right? How many of these possible there?
Right.
Try to include all of them.
The other thing is, I guess in those papers they never include, a spin orbital coupling. So
right, maybe
which might affect the phase diagram once that is included. And in your system, SOC is substantial, I think.
Yeah. Oh, I'm not saying we realize this phase. Now, okay, from now I will talk about experiments, which whether you think they are related or not is your taste, but we really ask the same question: can Luttinger liquid physics survive in a 2D system, right? And this is my review of theory background. Now I'm going to talk about the experiments, which are independent, right? Okay, so the material system we talk about is tungsten ditelluride. It's a material that we have been studying for a number of years. It has many unique properties. I'm not going to go through all of them, but quickly remind you of the crystal structure. What I'm showing here, top view, is the is a 3-layer of atoms: Te, tungsten, and Te. And the blue here is Te atoms, and red is tungsten. This system has a rectangular unit cell, as I shaded here. So a single layer of tungsten ditelluride, it's by itself is the insulator, which actually we do not fully understand what's going on in the insulating state, but we know it's insulating state, very strong insulator, and has been characterized as a quantum spin Hall insulator and also external insulator very recently. If you dope it, it becomes a superconductor, and so on. There's a lot of interesting property in this material. What I want to highlight today is this. If you look at my the red atoms of W vertically, you see zigzag chains, right? So the tungsten ditelluride tungsten chains already like Quasi-1D. So that's given from the monolayer. So it would be more clear if you visualize this material experimentally. The first imaging here is the transmission electron microscope. Really look at the lattice, atomic lattice, where the bright spot is a tungsten atom. You can clearly see a single layer of tungsten ditelluride has this Quasi-1D, has a 1-dimensional chains here. And the image on the right is the STM topography, which means there's an electronic state that you can also see 1-dimensional chains very clearly. So monolayer tungsten ditelluride is difficult to study in a wide range of doping, especially near charge neutrality or hole sites, because it's very insulating. And the quantitative measurements of insulating states in resistance, for example, it's quite challenging. So what we try to do here is to put two layers together so that the sample become less insulating. What I'm showing here is a Moiré lattice. If you put two of them together with a small angle. So the top, now you see, so you have 2 layers of tungsten ditelluride, so 6 layers of atoms. You already see the Moiré pattern here, right? Therefore, I actually give you the stripes perpendicular to the original zigzag chain of the monolayer. On the bottom slides is a same Moiré lattice, but I only show you tungsten atoms, so only to make it more clear to see. So what you see really here, if you have a 1-dimensional chain in an array and you twist it a small angle, you have a Moiré pattern in the perpendicular direction, as I shown here. So the twist angle will determine the size of the unit cell. So the monolayer has a rectangular unit cell. Here, the twist bilayer also have a rectangular unit cell, but it's big. And the twist angle will change that unit cell, the size of the unit cell. If you think is as a stripes, it will change the distance between stripes. And we are interested in this talk a small angle near 5 degrees to give a dimension. Near 5 degrees, you see the distance between the AA spots or interwire spot. The distance is D, it's about 7 nanometers. So you already see that this Moiré pattern actually realized, right, to some level, is very closely related to the pattern that I show you in the background introduction part. So
is there a special reason why you choose 5 degree instead of smaller or bigger angle?
I will show you what happens smaller angle too. So in general, between I would say 2 to 3 degrees to 10 degrees, physics is similar, but they have some variations. I will show you. Okay. If you go above large angle, the physics can be completely different. So,
okay,
there's no magic angle, so the small variation is fine. Okay, so the experiment is really done by these two heroes. They really done all the works. Peng Jie Wang is the expert in all aspects of we talk about, from fabrication to measurements, low temperature measurements, and so on. Boy is the graduate students, also excellent students. I'm really fortunate. So what they have done is to first perform a conductive FM image to check the Moiré pattern. Okay, so this is nothing but so just like STM. So but it's performed in the FM machine at room temperature to check the Moiré system. That's what they find. You can already see the patterns that is very similar to what I have drawn you in PowerPoint. Right? So you can zoom into here. So they aim at 5 degrees, end up with 7.1 nanometer distance. I told you it should be 7.2. It's very close. And you can see the rectangular unit cell. And then to study the physics, we fabricate this kind of device in this geometry where we have top and bottom gate and boron nitride fully encapsulate the system to make high quality. The material is kind of air sensitive, so that we really have to encapsulate them. And also they are edge mode for the monolayer, right? So a lot of fabrication process in graphene we cannot do because it's air sensitive. So that's why we have invented this geometry. Where what we really want to do is to put contacts only to the middle of the twist part in the ring structure so that we can study the anisotropy. So we want to do is something like this. From source to drain, we pass current. We may want to measure voltage from other probes and so on. So once we make this kind of device, it's very robustly reproducible or very easy to find that the transport along different directions is very different. What I'm showing here is that the transport measurement, the 4 probe measurements, the contact configuration is shown here along 2 orthogonal directions. One we call hard because the resistance you see here is much larger than the other direction we call easy. And the same plot, one is a log scale, the other one is just near scale. You can see that in the whole side or near charge neutrality to the whole side, you see a huge difference between them. About 1,000 times different. On the electron side, however, is very close. So really, the anisotropies belong to the whole carriers and not the electrons. Also, it's the proof that it's not because the gate tunable is very good contrast experiment. It's not because of some artifact in the device. It is the whole carrier that produces strong anisotropy. And we can also, by now, we reproduce this in many devices. Here's 2 of them. At low temperature, you see strong anisotropy of near 5 degrees and 6 degrees similar. Also the gate dependence. So really the red here is a very strong anisotropy up to 1,000 if you divide the resistance of the 2 directions. The blue here is no anisotropy, right? That's the electron side. So the other important aspect is that it's not just the resistance value they are different, they really behave qualitatively different along the 2 directions. What I'm plotting here is one device measured as the same plot, the resistance function density, measured as function of temperature. If you look at the hard direction, when you cool down the temperature from 200 Kelvin to 1.8 Kelvin, you see the resistance increase very quickly, right? That looks like a strong insulin state, right? And in the easy direction, however, it's not really changing much, or at very low temperature, you may even see the lower, goes down, so like opposite trend. So it's really qualitatively different along the two direction. Very similar behavior is seen in other devices too. So the conclusion is that, right, what's going on in the material, why you have so strong anisotropy in the whole site, and why the transport is so qualitatively different? Do you have 2D array of one-dimensional channels, right? That's what we want to study. And most important question will be, is there Luttinger liquid physics in this system? So as I mentioned, there are two important aspects of a Luttinger liquid. One is the power loss suppression of density state. The other one is spin charge separation. So we so far don't have any evidence on spin charge separation, which I think is a very interesting or exciting direction to explore in the future. We can, however, reveal the power loss suppression of density state. Experimentally, this will convert to the transport behavior as following. So if density of state is proportional to e to the alpha, alpha is the exponent, right? Then conductance should be proportional to t to the alpha, because t provides the energy. Or you can also measure as function of bias, voltage bias that you applied. In this case, we should measure differential conductance, which will also reveal, should also reveal the same exponents that reflect the interaction and the suppression of the density of state of Fermi energy. So this type of measurements has been performed in the previous one-dimensional system, right? The single carbon nanotube or other system. What's measured is the conductance as function of both temperature and bias, and then you want to see whether they really, in the scaled plot, collapse to single curve, so that you do have evidence of power law suppression of density state. That's something very similar that we have measured, but in our case, we have a one-dimensional, we have two-dimensional array of 1D wires. So the easiest geometry for us is to measure cross-wire conductance, just measure along the hard direction. So you are actually thinking about tunneling between Luttinger liquid. Right? So in that case, you should also see the power loss suppression of the density of state. So that's what we're going to show here. So we parked the gate voltage to the whole side where you see strong anisotropy, and you measure the conductance along the wire. So immediately you already see the data here, the conductance as function of temperature in a log-to-log scale. So linear is meaning power law with exponent alpha around 1 in this case. You can also check differential conductance as function of bias and temperature. In this plot, I'm showing you a variation of bias by more than 3 decades and temperature by more than 1 decade. And you can see that all this data is the raw data. We just record the voltage and divide by the current. They collapse in a scaled plot where you only involve a alpha t to the 0.98 in this case. That all data collapse into this same line. So this really saying that the conductance of temperature or as far as bias, they are dominated by the single exponent alpha, which is same, right? So that's why they can collapse. So the single alpha exponent is really a key in demonstrating the Luttinger liquid characteristics. We can also vary the so these are plotting of 2 devices by changing their density. So we can use a gate to change the doping. As long as you are on the whole side, you have very strong anisotropy and good power loss scaling, as you can see here. And I give you some examples, right, in this device where we choose different gates, and you see the alpha can already be changed. So alpha can change from 1.15 to 0.96. This one is not too much, but the other device change even more. That this single exponent behavior also survive for different alphas over a wide range of doping and different samples. Here's another sample. You can see the alpha can change from 0.7-ish to 1.2. So as long as you're on whole side, we see good power loss scaling down to, in this case, 1.8 Kelvin. Yes. How we start a bit late. Do I have more time?
Yes. Now it's 25 minutes.
Right. So I still have 25 minutes.
You got. I think you got 15 minutes left.
I have 15 minutes. Okay, good. That's good timing. So we demonstrate a wide range of doping, in whole doping, that the physics here can be described by a power exponent alpha, right? And of course, there's a lot of needs for theoretical modeling, how to understand this phenomena, why have such strong anisotropy here. And in particular, so we have some modeling with our collaborators, Sid Paramascan and Shivaji Sandhi, where they did some single particle calculations, not including the interaction, not the SOC yet, but it's just try to start modeling the system, which is the result saying that's very difficult to model the system as too many atoms and many interaction SOC make everything complicated. So we certainly needs much more work on theory, try to understand what's going on. And in particular, we need to understand what's the real connection to the sliding Luttinger liquid that I mentioned in the beginning. Are they similar phenomena or maybe different ones, right? So this is a very interesting question that we should, I feel exciting. But let me look at the interaction effects further. I go back to the introduction part where we have naive, intuitive, let's say, understanding of the system. So first of all, we mentioned that you need to have large eta, right? Which is the interaction reflecting the interaction strength of the Luttinger liquid in a single wire. Now we measure something alpha here, which is exponent of the transport data, right? Like T to the alpha. So in this case, we are talking about tunneling between parallel wires, so that two Luttinger liquid wire will give you one exponent eta, you should have two eta, right? So the real transport T alpha here, alpha should be 2 eta, and it has theory here do more careful calculations. But we have to also be careful how to really apply to the system that we're talking about here. But the theory would suggest alpha equals 2 eta minus 1, considering the device, the geometry that the wires are parallel to each other. So if you use this formula, it's saying that if your observation experimental data where T to the alpha is about 1, then you get estimate eta in the wire effectively is also 1. So that we're actually very close to the transition. We are in a very good range, saying that interaction could be strong enough to stabilize a 2D Luttinger liquid. And you see that eta, the alpha that we measure here is close to 1, right? So, but the real question is, can we demonstrate at even lower temperature, go to millikelvin, right? So that's the key. Go to the experimentally accessible lowest temperature to see whether this physics survives. And that's what I'm trying to show here. In a new device near 3 degrees of twist constant ditellite, same material, but different, smaller twist angle. The smaller twist angle means larger unit cell. Right, so you can say a lower energy scale for the hopping term. So we see very similar phenomenon, but at lower temperature scale now. So previously in the 5 degree-ish, at 2 Kelvin, we already see very strong anisotropy. Data showing here is the anisotropy assumption of gate voltage, but at 2 Kelvin now we don't have much resistance, also very low, kind of metallic. But once you cool down the device to millikelvin, the anisotropy quickly develops to more than 1,000. And if you look at this device, again, along the hard and the easy direction, you can easily identify them. So hard and easy differential resistance as function of bias, the same kind of measurements, but along different direction, you can clearly see the difference, right? In this case, where the hard looks like insulator, now the metallic state, the easy direction looks like metallic or even superconducting case, right? So the different dVdi as function of bias, you have a peaks, but it's not superconducting. Here's a Luttinger liquids. So as long as you see a curve like this, you must be, oh, there's something very interesting. So you increase the bias, you will suppress the states. So this saying that you use a bias to kill the Luttinger liquid physics. It only happens at low bias. And also you can check the power law exponent for this device. So you see good, power law of the conductance, where alpha now is 1.5 in this case, and also scaling behavior quite well. So I think it's very interesting situation where we can try to answer this question, which is, can you have emergent two-dimensional large liquid-like phase down to the lowest temperature? I would say, why not, right? So in this experiment, it seems that we find at least down to 50 millikelvin, we can have such kind of phase. And then we'll be very interested to ask what happened next, right? What happens if you apply magnetic field? Can you observe superconductivity, or what about spin-out, right? Spin charge separations and so on. So that's something next to explore, but I will give you very quick, this is a theory background, again, what may be done in the system. So this is one last slide before we may end. So if you have a coupled Luttinger liquid, a lot of theory papers are listed here, many of them actually from China Ken. So you think about apply field to the wires, coupled wire system. If you have a zero field, each of wire in the simplest settings is just one parabola. So that if you apply magnetic field, you're going to introduce a vector potential A, which will shift, right, the momentum of each wire for this parabola. And you're going to shift them differently for different wires because they have different distance to the first wire, right? So you get something like this. And then you turn on interaction between wires. You actually, you can open a gap. This really looks like quantum Hall situation. You have, gapless edge mode and gap bulk. But this arises from non-thermal liquid. Right? So can you observe quantum Hall effect in this case? That's a very interesting next direction to explore. Also spin charge separation and so on. But this is one of the big, this is one of the examples I would like to point out. But in general, I hope I have convinced you that this interesting system, tungsten ditelluride materials in the 2D, in the monolayer twist, have many possibilities, where now we can combine topology, fractional laser, non-thermal liquid, and so on. So that's the end of my talk. But of course, a lot to do with experimental theory. So I would like to, at the end, acknowledge those people, especially Peng Jie and Guo, who really did the work, and also everyone in my lab that support everything we talk about here. And lastly, Shrup, Bob Kawa provide us really the high quality tungsten ditelluride crystals to make this possible. And we have a lot of discussions with Seed and Shivaji and our boron nitride crystal from everyone from the Japanese lab. Well, thank you all. If I can take questions. Yeah.
Hi, Sanfeng. I think the data is really beautiful. And I have a quick question on, have you ever talked to any STM people? Maybe they can do some local measurement, for example, the local tunneling density state.
Yes.
Right. That if they can move the chip, that might verify your picture. Right. So what's the origin of the Quasi-1D chance, right?
Right. Yes, we talk a lot with Ali standing here. We have done the experiment on the monolayer case where I showed that one of the image is from his lab. Actually, we collaborate. But there are technical barriers that we have to overcome in order to really do it. It's on our list. We're both very interested in this. You can think about if you can do a low temperature STM and then vary the gate tune it from electron side to whole side. I'm sure you will see a big changes and see the patterns. The material is air sensitive, so there's something we have to develop before we can do a high quality data out of this. So, but that's ongoing.
Yeah. The other question is, since you have this gate to tune the density,
yeah.
Do you have any results or maybe comments on twisted superconductors?
Twisted superconductor.
Well, I mean, each modulator is a superconductor, right? If you electron dope the system.
Yeah.
But now if you actually have two of them twisted, right?
Right. We see hint of superconductor in this material. I think it's something I cannot say very conclusive now. I'm not surprised if we see superconductivity in this material, right, at all. In the twist, monolith we already know it's superconducting, but in twist, we see some hint already, but it's hard to say more than that. So
okay, so basically you mean in bilayer, in twisted bilayer, the superconductivity is not that it's more complicated than the a single layer one.
Right, whether one that related to the mechanism. In experiment, you see it, right? That's more interesting is that are they the same pairing and this and that, that's the theoretical part. But that's even more advanced questions. In experiment first, you see, can use, so let me put it this way. So in monolayer, we can easily tune it to superconducting states by add electrons, 5 times 10 to the 12. In natural bilayer, we never see it by the largest gate voltage. Well, if you can dope more, you may still see it, right? But so far we have not seen it in natural bilayer. In twist, we see hint. We start to maybe.
Okay. Good luck.
Yeah.
So my final question is, David Gobden observed this spontaneous polarization.
Yeah.
In bilayer, I guess.
In monolayer.
In monolayer.
Which one?
In multi-layers, there's layer dependence.
Oh, the ferroelectric.
Yeah. So in your case, let's say you have this AB region, AA region. Right. So
we sometimes see it, but not most of our devices in small angle twist, ferroelectric is if the Z is very small, we don't see clearly see it. But in bilayer and field layer, we do see it. You do have ferroelectric is expected here, but somehow in the small angle twist, we don't see it consistently. We don't see. We cannot conclude that even if Z is small.
Okay, so the reason I ask you is because if there exists some polarization in your Moiré structure, that can also affect the formation of the couple-langer liquid.
Right.
Physics.
Right. But this is not the first effect you're gonna see in this small angle twist. That's the experiment. Yeah.
Okay. Thanks.
Yep.
Do we have any other questions for Dr. Wu? If not, let's thank Dr. Wu again for his nice introduction on the impressive results. And we can move to our next speaker. For our next speaker,